So hello everyone, welcome back to this class. So in last class we have seen the Bode plot and we have seen little bit theory, and also I suggested that you go back to my flight control system class and understand the theory of the Bode plot. And from this we have also have considered so many example, and I have drawn the Bode plot and I have tried to explain the same. Now in today class what we will do, we will explain you about the root locus. So as you might have aware, in my flight control system class, when you have some kind of plant here, for example, let's say this is a plant, okay, and this is the input and this is the output, okay, and you are interested in output by taking the feedback, and here you are changing the gain actually, okay, this is your desired set point, and by changing this gain actually you can manipulate your system damping, right, by taking the feedback and all. So when you take this gain and you will change the gain, then you will see your closed loop eigenvalue will change, okay. So we will see in the today class how we will achieve the same, right. So what we will do, let's say we will consider the spring mass system with a very light damped. For example, in last class we have considered the 0.05 damping, right. So this okay, what I will do, I will uncomment this root locus first to see the plot, okay. So now this is the plot is coming, root locus. Now you can see how, what is the meaning of this plot, okay. As I said that ki cross mark indicates that the location of the pole. So now in this case what was the system, 1 upon s square plus s plus 1, right, spring mass system, right, where m equal to 1, c equal to 1 and k equal to 1. So what is the root, what was the root, you have solved this quadratic equation, you have found out the roots, right. So the location of the root is two roots conjugate, and the root location is minus 0.05 plus 1.08 I. What was the damping, 0.05, right, we have considered 0.05 only, right, damping it is showing, and location is minus 0.05 plus 1.08 I, and gain you say 0, right. Now the gain is 0 because this is a natural uh, uh, location, you have not manipulated, okay. See this, this was your plant, right, and this is the input, this was the output, you have taken the feedback h, and this is plus set point, and you have given some set point, and you are compressing and taking the error. So now you are changing the gain h. What is the closed loop transfer function, when you g divided by 1 plus gs, right, when you put h equal to 0 you will get the open loop transfer function, right. Now when you change this gain h, actually you will be able to change your pole location. So when you put h equal to 0 means what, gain equal to 0, right, what you will get, natural response, root location, right, and what your damping considered 0.05, right, it is showing here, right, okay. But see overshoot 85.4, large overshoot, right. Now what you will do, you will take this cursor here and you will try to go up direction. When you are increasing the gain, you are able to actually change this what you say, overshoot and damping, but as long as you are increasing the gain more and more, you are actually making the system more oscillatory, right here. Okay, so have you observed, by taking the feedback of actually on a spring mass system, you will not be able to control the system in a proper manner, only taking the feedback, right? So you have to use the PID controller in a proper way in order to control your system. But see, one more thing I said that the when you change the gain from 0 to infinity, okay, you are actually going from where? Open loop poles to open loop zeros. But do we have any zeros here? Do we have any zeros? No, right? So that is why you are going to the infinity. Now what I will do, I will put one zeros and we will see how it is coming. So what do you think? Should we put zeros on the left half plane or right half the plane? Right half plane we will put. Okay, we'll put one zeros here, which is see this. Now see this. Suddenly the graph changes, right, root locus? I have put one zero here. See this. This zero I have put one. S equal to plus 1 I have put 0. And now see, when you increase the gain, it is coming and going into the open loop zeros, right? You can on the grid, okay? And see this. When I will take the cursor here, what is this indicate actually? Open loop condition, right? And when you are increasing the gain, now see, when you have a zeros, you can actually improve your response. See, if you want to be critically damped, you can place your pole here. So damping is 1, overshoot is 0, perfectly critically damped. Okay, let's say if you want to attend this, you are perfectly critically damping, right? Here, damping 1, overshoot 0, you have frequency 0.5, and but in order to achieve this, what gain you will put in the feedback? 0.798. So this is the beauty of root locus. By moving this point in the MATLAB, you can see how you can achieve a proper response. And now when you further increase, what I said, when you gain from increasing from 0 to infinity, it will goes from open loop poles to open loop zeros. So when I will reach this point, what will be my gain? Can anybody tell? When I will reach this point, what will be my gain? Infinity, right? So let's check. I will directly infinity. Agree with me? INF, infinity, right? And since you move to the right half plane unstable, that is why it is written damping -1. Okay, and each line, this radial line correspond to the damping, because when you have plotted the this root on a complex plane, for example this root, right, zeta omega n plus minus omega n under root 1 minus zeta square, and this is I here in a complex plane. When you plot this, what you will get, you can locate the root where you can see this is actually one omega n, and this is, you can say, theta, and cos theta equal to zeta, and each radial line corresponding to one zeta value, right? You have seen this, right, in a theory part in flight control system design. I request go back and revise the same. Okay, so that is why in root locus also, in MATLAB also, you can see each line represents the one kind of damping. Okay, so when you move along this line, your frequency will change, but your damping remains the same. In theory part also we have seen the same, right? Okay, So now I have shown to you how the root locus in a MATLAB, and what I said in the theory, when you increase the gain from 0 to infinity, the open loop poles will move from the open loop to, when you increase the gain to infinity, okay, that I meant to say ki when you increase the gain from 0 to infinity, okay, you will be actually moving from open loop poles to open loop zeros, and that is how I have shown in the diagram, okay. And depending upon your response, actually you can actually freeze the point. Let's say you have start moving in this direction, there, and when you reach this point, you say, wow, beautifully, I got the critically damped response, damping 1 with this frequency, okay, freeze this point, okay, I want to locate my pole at this point, okay. But when the first case happen, then you are going from the infinity, right? So you're, by taking the feedback, you are not able to control, but 1 zeros you have put, and you perfectly you have control. So that is the beauty of adding the zeros, okay. And what the PID does, have you ever think what the PID does? What is derivative? S. What is integral? 1 by S, okay. So if you solve this, what you are doing, see. So 1 by S plus S, if you solve, S square plus 1 divided by S. So what you are doing? You are actually adding the 2 zeros and 1 pole at origin. So by doing this, actually you are able to control the system. And let's say if you add a proportional any value, for example, let's say I will add, let's say 1, then you can say S square plus S plus 1 divided by S. So you can see S square plus S plus 1 divided by S, okay. So that is the PID controller transfer function, you can see, okay. You can call as a G of C. So PID controller is also some kind of transfer function, right? Depending upon the Kp value, Kd value, this coefficient will change, right? Kp, Ki, Kd value, right? But here what you are doing, you are actually adding 2 zeros and 1 pole at origin and 2 zeros at some point, and you are making the system stable. So that is why I have added 1 zeros here, and you are able to control your system, okay. So that is the beauty of PID control. You can think the PID control in this way also, okay. Let's see what will happen in the case of spring mass system. So in spring mass system, you don't have any real part, right? You are having only omega imaginary part, and you can see here you have a 2 pole at a imaginary line. And what is the lambda? What should be this point value? Can you tell me? Anybody can tell me? Just 1, right? You see, real part 0 and imaginary part 1, because when you write the root, you will write the root like this, right? Minus zeta omega n plus minus I omega n under root 1 minus zeta square. So we will put zeta equal to 0, so we will get 0, and here omega n is under root k by m. So k is 1, 1 is m, so you will get 1 radian per second here, okay. So you will get 1 I, and you can see you are not able to control by taking feedback, and overshoot is 100%. You are keep oscillating, neither diverging nor converging, right? Do you think when I will add some zeros here, you will be able to make the system stable? Like in previous case, we can do this, right? What we will do? We will add 1 zeros here on the right half plane, okay, and you will see how you are beautifully you are able to control, okay. So this was my original position, and now you will see you can actually critically damp, or if you want to, or let's say the criteria is overshoot should be less than 10%. So let's say 9. So you can actually freeze this point here. You can select gain 0.7 approximately, here is 0.681, you can take 0.7, and then actually you will get the damping 0.6, and overshoot is less than 10%. So let's say your requirement is I want to design the control system with a 10% overshoot, and damping should be damping around 0.5, 0.6, then actually you can freeze this point. Okay, so that is the beauty of root locus. Okay, and how you can use actually MATLAB in order to save your time. But as I said, always please try to understand theory and then go back to the MATLAB. Then only the MATLAB will support you. Okay, so thank you so much. We'll meet in the next class. Thank you.